Hi there, welcome to the continuation of tutorial 9. So in this case, we're going to run now the demonstration, so see what is going on here. So first, we're going to run this simple case, okay, very simple, but don't be fooled because look at the Reynolds, 10 million. So this is where Reynolds Turbulence modeling counts. So if you run this case laminar, you will see that you're going to get completely the wrong results. I'm going to run the 3D case, okay, or the pseudo 3D. So I open Fluent in 3D mode. So I will read the file. Okay, in this case, I will read the case file, but I have already this set up. So Fluent case. So this will work in Fluent 2021 or Fluent 2020. All those versions, you will need to read the mesh and the settings in the previous video. So I will go ahead here and read the load remesh. So this is an expensive case. Okay, so we'll run this and reading. See here all the information, everything, the case setup. And now we can go here in mesh and let me go and plot the mesh. Okay, so see, this is what we have, front and back faces. So let me put the back face showing you the outlet also. So what is, okay, I don't want to see the front. So remember that we're on the bottom. What we're doing here is that, see that one cell here, and here we have sleep, no sleep. So on the flow, when the flow arrives here, you will have the boundary layer develop. Okay, so the Reynolds is super high. So here we don't have any transition, or if there is a transition region, will be like 1% of this region or even less. So in the next video, we're going to talk about transition, and we're going to see that we can resolve the transition. But in this case, I'm quite sure that this super high Reynolds number, there is no transition. So the case setup. Let's visit the case setup. So always I like to follow the vertical workflow here, where also you can set up here for the ribbon and even from the text user interface. So here we have models. You can choose, at this point we have seen all the models. So let's run a first iteration using the classical decay omega SST. That probably is the most general one. Okay, that you start to run all these cases, you will see that this one will give you always relative good results. Instead decay epsilon and the others, you will need to tweak something. So nothing else to do here. Materials, choose your working materials. Okay, so in this case, we're choosing the properties. Sorry, we're using Reynolds number analogy similarity. So we can change these values to get the Reynolds of 10 millions. Okay, it's up to you. Okay, so the Mac also is also in the experiments is really low. So 0.15, which if I recall, so that is counts as incompressible. It's the one you can run compressible. So here in set conditions, the reference pressure, so some conditions, and then we go boundary conditions. Okay, so remember that the back and front needs to be symmetry. Okay, to make it 2D. The bottom is this one, is the wall, and see that this is slit surface. See that there we have it as a symmetry. Okay, no boundary layer, and then right here and you have the development. So then you have the top, that is also a pressure outlet, or you can put also a symmetry there. It's up to you. In this case I chose pressure outlet, but probably it's not the best one, but it's up to you. You can play with that. And then the outlet is also pressure outlet, and then we have the inlet. Okay, so in the inlet you set your values. So using the fluid properties and this velocity, see that we can, and the given length of this flat plate, we can get the Reynolds number. And see that we're using also relative high intensity and viscosity relative values. Okay, so you can play with different values and study that dependence. So we keep reading here. This is, remember to compute coefficients. In this case, if you want to compute friction coefficient, you need to give the right values, otherwise it's not used for anything. So then we go solution methods. As I mentioned, I recommend always to use the default method, but it's one you can use different methods. In this case, it's relatively inexpensive, so you can see the difference in convergence speed, but you should get actually the same results. I'm sure in this case you will get it. So the couple is usually the fastest one. Okay, and most stable. Controls, default values are okay, but remember, if you have problems with the stability of the turbulence model, try to reduce these values. Okay, the relaxation related to the turbulent variables. Reports definition, you set all your monitors. So see that we have 6 monitors here, and just to show also something as well, that I have a line here, and in this case, let me the outlet erase. So see that I'm sampling in this line here. Okay, so I'm sampling all the quantities there. So see here that I created these monitors here. So I have this report definition to sample wall shear stress here at the wall, raw mu, that probably is constant, so you don't need to put it, but just to show you. So basically, look at that. What I'm doing here, I know the wall shear stress in the whole domain is 0. So basically, compute the maximum, vertex maximum. Okay. And then I have the monitor for average Y plus. Okay, so see that the average Y plus, the mass flow at the outlet, and average velocity, I think, also at the outlet. Okay, so set up your monitors, very important. Okay, your reports definitions, everything will be plotted. You can choose to save everything as well. And at this point, we can run. So if you go here, let me initialize. Okay, so we have the initialization. And let's get reading. So remember, to create lines and points to do probing, you can put it here in surfaces. In new surfaces, so new, and then you create it. Okay, so see that you create a new line. You need to give here a starting and end point, and that's all. Okay. Then I would like to move here in parameters customization. See that I created already many custom fields. Okay. So just let me revisit the custom fields that I have. First, shear velocity. So see that is computed using these monitors that we created here. So we're sampling here at the wall. So remember that we created those monitors here. So see that you use it to compute shear velocity. Then the U plus, okay, using the previous computed shear velocity, you get also magnitude, and then you get this quantity, and then you compute here the Y plus normal to the wall in this line. Okay, so see that we're sampling this shear velocity Y. Okay, so I know that my coordinate here is 0, so I don't need to do any transformation there. And then divided by mu, and you have it there. Same here for the shear stress. Okay, remember the shear stresses will be responsible for the momentum exchange for the mixing in the boundary layer. Okay, so we have a laminar one that can be computed strain rate times laminar viscosity, and the other one is strain rate magnitude times this is the total viscosity, effective viscosity, and strain rate magnitude times turbulent viscosity. Okay, so this is how you compute it. So here, when we put the effective viscosity, okay, is laminar times turbulent, but we can also create a new one. This plus this one is equivalent. So we compute this one and we can do the plot. So we do all this because now we would like to do the classical plotting here, the loads, the wall, and everything. So when we run, I will show you that inside Fluent, but also how to save the files and do the plotting outside. So if you go to the website, see here that you have the notebook, and in this case, I did the plotting using Python and Bokeh, I really like. So you get this information, probably you get Peter plots that the ones you get in Fluent, but pretty much the same. So see here that I have everything interactive. So you have the case, okay, wall resolving or wall modeling. Okay, so we can do all this plotting. See that we compute here velocity profiles. So let me go here soon in function of Y plus, and see here the importance why when you use wall modeling, you need to put enough points in the logarithmic region to resolve the velocity profile. Okay. And all the plots here, okay, this is enormous to the wall, to kinetic energy. So we have seen that this one peaks in the buffer, somewhere in the buffer layer. So you see that you have this behavior. And then look at that in the wall modeling, all this region here, you can see clearly that has been modeled below here, okay. But nevertheless, that we are not capturing this phenomenon here. Okay, the wall function is actually enough to get a good value here and then a nice prediction on the rest of your profile. Okay, so we just save this data from Fluent and plot it here. So let's run this case. So nothing to do. So see that we have all monitors, we initialize, and let me press here, run calculation. If you want to sample statistics, up to you. Okay, so press that. And now it will start computing. So you have all your residuals, everything is converging nicely. Okay. So probably here is a nice case because if you run using the segregated solver, you will see that the cost per iteration is much slower. Okay, so it's nice to test the efficiency or the convergence speed of these solvers. The cost per iteration tends to be a little bit higher, but they are more stable, generally speaking. Remember that they use much more memory. So at this point, let's wait a little bit until we reach convergence, and then we keep working on this. Okay, at this point I reach my tolerances. I have a converged solution. So see that in this case, now this is a nice validation case because also you can push your solver to reach low residual. So these are rather very low residual. So usually 10 to the minus 4 is a good industrial value, but here we're going to 10 to the minus 5 to reach a very good convergence rate. So see that set here is very low. See that it's almost machine precision. Remember that we're not solving this one. So in theory, we don't need to plot that. So if you don't want to plot that, remember you go in monitors and just deselect here that and put plot, and then you have it here. Oops, sorry, I chose the wrong one. Should be this one. And there you go. Okay. So look at that, my velocity average. I have a monitor in the outlet. See that everything is stable. The mass flow is also stable. Okay, so remember you compute the balance between inlet and outlet should be 0. It's conservative, the method. So here is just measuring at the outlet. And your average Y plus, so see that this well resolving relative low value. So just to show you that now you can go here in reports and you can do more stuff. So you have fluxes here. So see that between inlet and outlet and compute the mass flow. Okay, it's non-zero, but it's a low value. Okay, so always check that your method is conservative. So at this point we have the solution, and see the beauty of this one. What I like to use is because now you can go directly at the button. So see that you have the button and you can plot there in the surface and you can visualize better what you have there. So if you go here, for instance, with the Y plus value, see that you have now that quantity. You can get pressure and everything. So this is what I like, but it's up to you. It's a matter of preference. Okay. So at this point, we have all quantities. So see that if I go turbulence and total kinetic energy, and if I zoom in here, normal here, see that we are resolving. Let me hide this from the bottom. See that you are resolving boundary layer. Okay, so this is a very fine mesh. Okay, just back. Okay, and see that you are resolving down to the boundary layer. Okay, so you resolve this. You resolve this K profile, epsilon profile, all your profiles you can resolve. Okay. And remember also that what it say that a good criterion to see if your mesh close to the wall is good as well is just to put the Turing viscosity ratio, and remember that Turing viscosity peaks in the boundary layer. Okay, somewhere probably in the middle of the boundary layer, kind of. And this one also will give you the end of the boundary layer. So probably this will be the thickness, let's say, give or take. But see that this is a good way also to check that your mesh is good enough to resolve there. So the criterion is that the transition, see here in these peaks, should be a transition unit for that in this case. So for instance, you do your mesh and you have instructor cells. And let me show you that if you go, for instance, in this cell here to a cell like this, see that you have this cell center. Okay, a little bit. You have this cell center here, and then you go to this one. So see that you have this jump here. Remember that you are computing gradients and you are interpolating this. So this will add a lot of numerical diffusion. Okay, so always be careful of this. Okay, when doing your mesh and trying to get a good transition in your boundary layer to avoid this error. This will add dissipation, and this will be pretty severe if you have that here. So for instance, you have the cell center here, and then you go like this. See that you are interpolating values from here, and here we are already close to the wall, okay, to the viscous sublayer. But see that you will be introducing some turbulent viscosity in your viscous sublayer due to this fact that you are not controlling the transition. Okay, so be careful that those are the issues with meshing. Okay, so just addressing that, let's go to the post-processing. So see here that we have in the plots, we have all these plots that are already put for you here. So see that you can access. The solver will give you a lot of information. Okay, so the solver, see that you go to turbulence, will give you the production of K. So remember, in the theory we address those terms. You have everything. Okay. So remember, each model will give you access to some information. So as you use this parallel matters doesn't give you information of K because you don't have that information. In this case, we have K and epsilon, but we don't have the Reynolds stresses because we don't have that. So if you want the Reynolds stresses, what you can do is use a Reynolds stress model, or you can then switch to unsteady and compute those fluctuations, the definition that you can compute it. But in this case, we're not interested in that. Okay, so see here that you can plot production, all these terms, dissipation. So for instance, when I did these plots here, that we have production, dissipation. Okay, I just read in the data from Fluent. Okay, so in Fluent, if you want to save that, you go here, write points, press write, and then just give it a name. So in this case, let me call it test. Okay, and you write your data there, and when you go here, see that you have the test file there, and voila, you have your data. So you have here y plus normal and your turbulent there, turbulent dissipation rate, and then you just can use this data and plot it. Okay, so basically you save whatever you choose when you are plotting. Okay, so this is how you do it. So you have all these variables, and what is here, let's take a look at the U plus Y plus. Okay, so see here that we have the traditional profile. We immediately recognize that this is the right shape, but let's compare with the empirical values that we know. So usually remember that you load files and you will have validation data. Just here, ASCII data, love the ball. Okay, and let's read this data, and let's read the log and the viscous. We compare, see that we solve very well the viscous, and then also see here that we're also resolving the log region. Okay, so this is part of the validation, and see here that in this region, this is the buffer layer here where the errors are larger. Okay, so it's not clear how sins are done here. Okay, this blending. Okay, so this is what we try to avoid it. So you have all these plots. So see turbulent kinetic energy again. So see that it's peaked somewhere here. So this y plus normal. So you can do all your traditional plots. So, but in this case, let's see the shear stresses at the wall. Okay, so see that you have this, and we have the validation data. So as you go here again, should be ASCII data validation, and we have that information here. So it will be CF. Okay, this one, friction coefficient. Okay, so you read that one. Okay, we have it there, and we have a difference, and maybe I think, okay, yes, it shouldn't be that value, it should be this one. Sorry, it should be this. I was reading the wrong parameter. Okay, so skin friction coefficient. Okay, so see that I'm plotting here skin friction coefficient. I think here I was plotting on something else. Okay, so skin friction coefficient in that file, also you have the skin friction coefficient, and see that you have a very good agreement with other sources, but also you have here correlation, so you can plot that. So this is how you run this case. As you see, it's relatively easy. So now, for instance, let's run with another model. Okay, so let me go for this parallel matters. You set that one. Okay, and let's start again from scratch. Initialize from 0, and let me go here and press calculate, and now we have the new model. Okay, and off you go, the solver. So probably this should be much faster because you have less equations to solve. Let's see what happened, but see that we have a very good convergence rate. Okay, so it should arrive soon. So here we are already there, and voila, we are there. So see that as you compare with the KX, this one was much faster. And again, you will have access to your results, and I would like to look at this one, friction coefficient, and let's compare with this data. Okay, CF, and we plot and see that we have a good agreement. So there is a slight difference with the previous one, but pretty much we're in there, okay? And just to convince you the importance of turbulence modeling in CFD, let me go back here and let me choose here laminar. Okay, so if I choose a laminar model, I shouldn't get the results because this mesh is not good enough to resolve all these scales, okay? And even something that seems very trivial here, okay, so it's telling me that y plus is not computed, so let me deactivate this, okay, because the y plus is not computed in laminar, okay? I know why the guy from Fluent didn't put it, so you need to deactivate it. Okay, so then we have some custom fields that also this is not computed. So in particular, I need to remove this because we don't have the turbulent viscosity. So now I can run. See that we only have the exact equation, momentum, continuity. And it is iterating. And see that we have everything, but look at, well, this is not being monitored. Okay, so see that now, if compared with the Spalar matter, see that the convergence is much slower, even compared with the K omega, but it's getting there, okay? So let's see, we'll get there soon. Well, soon, no, still we need to reduce another order of magnitude, but this should be faster, this order of magnitude here. So we already see that the K omega is faster than this, and the Spalar was faster than all of them by a lot. No? So we're in there. Okay, so now that we have a solution, and as you go and look at the pre-colors, okay, you will see that you will have a solution there. Okay, something that looks nice, but when you go here, and let me plot this one, u plus, y plus, see what you have. So this doesn't look like the profile that we're used to. And why? Because this one is just blending to the laminar solution. So as you load your profiles here, so let me load the viscous and the log, you will see that that one is following your laminar solution. Okay, which is wrong. And now again, to convince you, we go here as we plot the skin friction coefficient, and now I load the data related to the validation there, this one. You will see that the one that we're computing is much slower because it's laminar, much lower because it's laminar. So it's the wrong solution, and there you see the importance of turbulence modeling. So as you go to viscous again back, you can play now around with the K epsilon model and see all this stuff. So as you go here and you use the standard with wall functions, and you know that this mesh is well resolved, you know that you are going to get wrong results. So let me show you, and let me reactivate this one. And I don't need to start from zero. I press calculate and start from this laminar solution. So see that we have this jump here. So it seems that it will diverge, but now it starts to get down. So probably it will be better to start from zero. So these are some cases that it's better to start from zero. Now, and actually this is the problem of the turbulence model. So see that the K epsilon wall resolving is having problems converging with this mesh. So but just to be sure, let me start from zero. Okay, so just erasing that solution, maybe that was the influence, but it's still, I'm sure that I'm not going to get good results because I'm using the standard formulation of the K epsilon with wall functions. And that one will have problems getting a solution with a wall resolving mesh. And as you see here, we already see here that we're having problems converging. Okay, so at this point, you could stop it, and you will see that again, as you go and start to do these plots, you will see that you have these strange plots. Okay, so you can let it run for a really long time, but it's usually you are not going to get the right solution. So the solution to this, remember, you can go, in this case, scalable wall functions will already give you good results. That one will find the intersection between the two profiles. According to your y plus, it will choose a treatment. So we know that our y plus here is low, lower than 10, something like that, and it will switch to resolve everything. And see that now it's getting convergence, okay? So let me stop here. Okay, arrive convergence, and if I plot solutions, okay, we have the plots here. Let me plot this one. We have this profile. See that it is not okay. So let me put here. Let me put this Spalding profile. See that it didn't do a good work here. So probably two reasons, or maybe it was too noisy, the solution that we have, the initial solution, or the scalable wall function is not good in this case. So let's go and use the enhanced wall treatment, that the recommended one, and let's see what happens. So see that now this one, the enhanced, this one says that it's doing a good job. So now you have that jump here in Y plus, we converge, and let's plot again. So if I go here, see that now it looks better. Plot this, and voila, now you have a better agreement, okay? So another case that you see very fast, very economical, so you can try all your turbulence models, get a feeling of this enhanced wall treatment, but see that what I was telling you, that the K epsilon requires you to know this, but instead you go to K omega, it doesn't ask about near wall treatment because it's Y plus insensitive. So this is why another of the advantage of using this method. So finally, the last thing that I want to show you, let me go here and use this simple method, okay? And just to show you initialize, just to show you that the cost per iteration, this one, is much lower. So as you recall the previous couple, and as you are running, you will see that each iteration takes some time. Instead here, it goes faster, but the convergence rate tends to be slower. So it will be a compromise, okay? But see that the couple was going down relatively fast. This one, see that kind of, it is stalled there, okay? But slowly it will go down. Okay, you have these oscillations there. And now see that start to go down. So remember, this is not an indication of that you have divergence. It's just problems in the solver, okay? So maybe you can try to reduce on the relaxations and to improve that. Okay, so see that Y plus starting to stabilize. Okay, so let me stop here, and you go here and you can reduce this. So let me go 0.7, 0.7, and 0.7. Okay, so usually those problems that you see there can be related to that. And now that using this, let's see if we manage to stabilize that. Okay, so this likely slow down your computation, but it will give you a little bit more stability. Okay, so okay, see that it's trying to go down, and then it goes up. Well, slowly it's going down. Okay, so see that clearly, you see that we reduce the under relaxations, and we're improving the convergence rate. Okay, but already see that this is taking more iterations that the couple. Okay, but the cost is lower. So probably the 300 iterations will be faster than the 100 iterations in the couple. It's up to you. So see that now it's oscillating, going up. Okay, so don't be afraid of this behavior. Okay, again, it is converging, so this one will take much longer time to get there. Okay, so let me stop here, and as you post-process now, okay, let's see that we should have something similar, but not properly the profile, because still it is converging. I can see that there in my profile. So if I go here, put this, save plot, see that it's still, here is okay, but still you need to let it run to get a good convergence. Okay, so this is the difference between the couple. Clearly you see that difference between couple and segregated. Okay, the segregated tends to be much slower. Okay, instead the couples are quite fast. Okay, so this is why I recommend use this one. Okay, but in some situations it might be better to switch to the segregated solver. So that's all for this tutorials. Thank you very much for your attention, and see you in the next video. Bye.